Okay. Hey everybody. This is the third question, third page here, and this is on solenoids and electromagnets. So electromagnetism and solenoids. Some of the other ones use electromagnetism as well, but solenoids are the big use of that. So A and B are referring to this picture here. You can see the hand doing the right hand rule on that to help you out. So the south pole of this device must be located at which side of this thing. Again, your fingers are going to curl with the coils now. So your fingers are the current in this, and then your thumb will point to the north pole of the magnet when it's conventional current, and it's that. So the south is opposite that, and so south would be over there at B. All right. This is an example of what? This is a good question. Obviously, the answer is electromagnet, A. But let's go through these other ones too. Permanent magnet is a device or a object that has the domains aligned with unbalanced electrospin. A ferromagnet is the same thing. It's a permanent magnet or material like iron that can become a magnet that has unbalanced electron spin and domains that could be or are aligned, depending on whether it's magnetic material or a magnet, they'll be aligned. And then a transformer, we didn't even talk about this unit. It's actually a really cool application. Transformers and wireless chargers use magnetism to transfer energy kind of from one coil to another, but that's not this thing, and we didn't study that in this unit. So anyway, electromagnet or solenoid or coil would be the key there. C and D are referring to these two different kind of diagrams here. So I'm going to grab my right hand. Again, this is not useful in the video because I don't know if it's flipped or not flipped. I'm going to curl my fingers up on the page, around, and then back behind that bar like I'm grabbing it, and it puts my thumb over to the left when I do that. Again, use the right hand, and that makes this side north. We are doing the label and location of the north and south poles, so that would make that side south. And then if I do the other one, I'm going to put my hands kind of palm facing towards me as I come up on the back part of that rod and come back around and grab and come over the top, and then coming down on the front of the rod on the kind of this side. And when I do that, my thumb is pointing to the right, and so that's a north, and that puts a south pole there. It doesn't ask to draw the field, so I'm not going to draw the field around that. Determine whether electromagnets attract or repel each other. Well, if I see a south and a south, that means they are repelling. Opposites, that's not an opposite. Same poles repel. All right. All right, so now student has an electromagnet that creates a magnetic field B. Determine how the magnetic field changes if you quadruple the number of turns and cut the current in half. So again, the B for a coil, this is from the sheet, is equal to the permittivity of the core material. So that's a mu. So that's that permittivity. What kind is it? Iron, cobalt, nickel, neodymium. Well, not neodymium, but whatever it would be. Permittivity of the core material times the number of coils times the current. So they're all linear. They're all proportional relations. So whatever you do to one, it does to the other side. So didn't change that. We're going to do number of turns quadrupled. So that'll be 4 times, so actually 1, right? It didn't change that. 1 times 4 times, what do we do to the current? We made it 1/2, right? That's the number of turns. That's the iron, and then we didn't change the permittivity at all, right? And so that would be 2 times as big. Yeah, that's simple. So then this, I really like this question here when it shows you the numbers for the permittivity here. So the table below shows the magnetic permeability of different materials, not permeability. I've been saying that wrong the whole time. Student claims replacing the iron core with nickel. So we're going to go from iron to nickel here. Would be more expensive, but would be a more effective electromagnet. Well, we can see that 600 is much less than 6,000, right? And so no, iron has a higher permeability. And so it would make a better core material. All right. And then another student claims that both copper and or iron can be used as the core material in the electromagnet, since both of them are metals. How would you respond to this? Well, again, the number's not there, but we've talked about it, that iron doesn't have all those properties that make it a ferromagnetic material. So no, maybe you could be more sensitive to the other student by not just saying, no, you're wrong, but you say, hey, no, I don't think so, because copper is not ferromagnetic. Right? It has no domains, and it has, well, it might have domains, but it doesn't have the unbalanced electron spin that's there. All right, that is page number 3.